Hello everyone, welcome to this video where we're going to be talking about batching and other flow interruptions. In this video, we'll specifically be talking about setup times. Economic order quantity model is something that I'll cover when we meet next week in person. Okay, so we'll talk about the idea of batching, batch production, and the impact of batch size on inventory. How do you choose an appropriate batch size? And if time permits, we'll do product variety, but we'll see. Right. So a production cycle is is something that you see where one production cycles happens one after the other, and all production cycle essentially look the same in the sense that they have the same setups and production time. So in a lot of scenarios, this is true not just in manufacturing setups, but also even in office or service setups in office, or say when you're looking at a call center. In a lot of these places, there is always a setup time before you can actually start working. So the setup time could be sitting down, wearing your headphones, dialing the numbers that you need to dial, and so on. So there's always a certain amount of time it takes for you before you can start working. So setup time is always important, and sometimes setup time can be very large. For example, if you're looking at manufacturing setups where you have large industrial size machines, setups can take a significant amount of time. We're talking about multiple hours, right? So let's take an example here. So what is the impact of setup time on capacity? And this comes down to the number of batches. So a batch is a collection of flow units, and those are the number of flow units that you're going to produce at any given point in time, right? So that's what a batch is. The capacity of a resource can be increased or decreased by increasing the batch size. So if you're producing a batch of 12, so this is the same example. So this is the example of a zooter that we were talking about in the videos from chapter 4. So in the videos from chapter 4, we were talking about the assembly process for a zooter. In this case, we're talking about the manufacturing itself, manufacturing of the individual pieces that go into the zooter. Now, let's say that each zooter requires produce steer and produce rib. So one box contains 24 ribs, and if you have a batch of 12, then one box will contain 12 steer supports and 24 ribs. So you need 2 ribs per zooter and 1 steer support per zooter, right? So that's what you need. So if you're producing a batch of 12, it means that you'll produce 12 steer supports and 24 ribs. Now both steer supports and ribs are produced using the same computer operated milling machine. Let me see if I can show you that. Computer operated milling machine, which looks something like this. This is the same milling machine that is used to produce both the steer supports and the ribs, right? So if you have a batch of 12, then it takes a certain amount of time. So when you move over from producing steers to producing ribs, it actually takes a while. So it takes 1 minute to produce 1 steer support, which we need 1 per zooter, and it takes 60 minutes to change the milling machine. So it's a whole hour to change the milling machine from producing steer supports to producing ribs. So each time you move from one producing one of these types to the other, you have to wait 60 minutes to recalibrate the computer operated milling machine, right? It takes half a minute to produce 1 rib, or a whole minute to produce 2 ribs, because you need 2 ribs in a zooter. And again, it takes 60 minutes for the setup process itself, right? So if we are producing in batches of 12, right, so we can calculate, it's very easy to calculate the total time and the capacity, which is the number of units that you can make per minute. If the batch size is 12, then the total time is 144 minutes, right? Because it's 60 minutes to set up the steering support, 12 minutes to produce 12 of them, 60 minutes to set up, and then 12 minutes to produce 12 pairs of ribs. And that gives you a capacity of 0.0833 units per minute, which you can then convert to number of units per hour and so on, but that's basically what you have. But if you have 60, if the batch size is 60 instead of 12, it takes 60 minutes to set up the ribs, 60 minutes to produce the 60 ribs that you're doing, and then 60 steering supports, and 60 minutes again to set up for the ribs, and then 60 minutes to produce the pairs of ribs. So now the capacity is 0.25 units per minute. And instead, if you did 120, you'll notice that the capacity goes up. So as you increase the batch size, the capacity keeps going up. So the question that you should be asking yourself is, well, why shouldn't we just have infinite? Maybe we buy 2 milling machines and just make each of them on each milling machine. But if that's not possible, why not just produce a very large number of steering supports at once and then produce a large number of ribs, right? So if I do that, so how do you calculate the capacity given setup times? So given setup times, capacity is batch size, right? Which is the size of the batch, either 12 or 60 or 120. So batch size divided by the setup time plus batch size times the processing time. So the total processing time that we have. So batch size times the processing time. Remember, processing time is 1 divided by the capacity that you have here. Right? So that's basically what that is. Okay. So now if let's say that we are operating in batches of 100 units, so it'll be 100 divided by 120 minutes. So why 120 minutes? Because setup time 60 minutes for one of them and 60 minutes for the other. So the total setup time is 120 minutes. That's how long the milling machine will not be producing anything. It's just being recalibrated, right? So 100 units divided by 120 minutes plus 100 units times 2 minutes per unit. So how many minutes do you spend to make 1 unit? That's the processing time, and that gives you a capacity of 0.3125 units per minute, right? So that's how many units you can make in a single minute. So that's the batch size. So why not just choose the largest batch size? So one thing I have to realize is that even if you choose a very large batch size, you still need 2 minutes per unit. So you can never make, the capacity will never exceed 0.5 units per minute, right? It still minutes 2 minutes, you still take 2 minutes to make a unit. So in a minute, you can only make half a unit. That's the best you can do, assuming there are no setup times. But there are obviously going to be setup times, right? So 1 divided by P. So 1 divided by 2 is the maximum that you can do. But that is only if there are no setup times. But because there are setup times, you cannot do more than that. Okay, so why not? Why not just have a very, very large batch size to increase capacity? The reason for that is inventory. So if you have a very, very large batch size, it means that you'll be holding a lot of inventory. And if you hold a lot of inventory, you have to pay inventory holding costs, and sometimes things can get spoiled if you have them in inventory for too long. Things can get stolen. So there are lots of important things to keep in mind. So it's not always the best to manufacture the maximum that you can manufacture, because holding inventory is a difficult process. Think about this. This is true even for, say, something like a call center. Right? So let me go back here, right? So why not just produce large batches? What's the difference between producing large batches and producing smaller batches? So so this is the example that you were looking at there. So the example is, let's say that Toyota is manufacturing station wagons and sedans, right? They have demand for station wagons. Let's say that the demand is the same, which is 400 cars per day. You have the same metal stamping process that is needed in the final assembly, and it requires especially long times. Just to achieve high level of capacity, the plant runs production batches and sedans for 8 weeks, and then 8 weeks for station wagons, so on. So they do 8 weeks for sedans and switch over, then do 8 weeks for station wagons, and so on. Right? So that's what you have. So if you have a demand of 400 cars per day times 5 days a week times 8 weeks, so you're producing 60,000 sedans first, and then you're going to move over and produce 16,000 station wagons, come back to 16,000 sedans, and then 16,000 station wagons, so on. But that does mean that you'll be holding a large number of sedans in inventory, right? So if the sedans are sold off at a constant rate of 2,000 cars per week, so if that's the demand for sedans, it's 2,000 cars per week. So on an average, you'll be holding 8,000 sedans in inventory as you're producing, say, station wagons, because you produce a large number of sedans to keep them aside, right? And holding 8,000 cars in inventory is not a cheap process, right? There's always going to be some issue if you hold a large number of sedans in inventory. So instead of producing 8 weeks of cars before switching, let's say that we produce 3 weeks of cars before switching, right? So we'll be producing, instead of producing 16,000 cars of one type and then producing 16,000 of the other, if we produce, say, 3,000 cars of one type, then 3,000 cars of another, 3,000 cars of one type, and 6,000 cars of one type and 6,000 cars of another, then the average inventory that you hold is 3,000, which is dramatically lower, right? So smaller batches mean smaller inventories, and that's the major trade-off that we'll be talking about throughout this idea of this chapter. In fact, when we talk about more inventory management stuff when we see each other next week, but that's the big trade-off. If you can produce a large number of items to get, say, some sort of a better hold on the fact that we have large setup times, it's good to produce a large number. But then if you produce a large number, you're holding a large number of items in inventory, and that is expensive, right? And that's the idea here. So if you look at coming back to the Zooters example that we have here, so remember that the assembly process for the milling machine requires a supply of 1 minute. So this is something that we didn't talk about before. Let's say that after you produce this, then there is an assembly process, and the assembly process requires a supply of 1 unit every 3 minutes. So when we say 1 unit, it means 1 unit of the handle, the ribs, and a pair of ribs, and 1 unit of the handlebars also. So that's the requirement that we have from the assembly process. So the manufacturing process. So let's say that we produce 200 units, right? So we produce 200 pairs of ribs every time we make it. Then as we produce 1 pair of ribs per minute, it only takes and assembly only takes 1 pair of ribs every 3 minutes. You're accumulating inventory of ribs at a rate of 2 ribs every 3 minutes, or about two-thirds ribs per minute, right? So by the time you produce 200 of these ribs, the number of ribs in inventory is about 266 ribs, or 133.3 pairs. So that's basically how many ribs will be in inventory. So that's the maximum amount of inventory that you'll be holding, right? So we did some of these calculations, if you remember, when we did the Wally's widget warehouse examples last time, right? Now, so remember that even though the rib process is a continuous process, there will be some idle time. So why is there an idle time? So for example, if you produce 200 scooters at 3 minutes per scooter, it takes 600 minutes. This also includes 80 minutes of idle time. The reason for the idle time is that you don't want to produce it too quickly, because the assembly takes only so many per minute, right? So the assembly can only take 1 unit for every 3 minutes. So if you can produce 200 components every 520 minutes, which is faster than we can assemble them, which is only 1 component every 3 minutes, right? That's something to keep in mind. So it's not always best to produce too many at the same time. The question is, how do we produce? So what is the best way to do this production? So remember that we have to produce ribs, and we also have to produce steers. So how do we do this switchover process, and how do we do this manufacturing? The best is to have this sort of sawtooth sort of inventory process. This is something that a lot of manufacturing facilities use at a constant rate. So with that, you can always calculate the average inventory, which is half the batch size times 1 minus flow rate times processing time, right? And you can sort of measure how much inventory that you hold. So first you'll produce ribs. So the idea is you manufacture all the ribs that you need to manufacture. You stop the inventory of rib manufacture. You take 60 minutes here. So you produce 200 ribs for 200 minutes. Then it takes 60 minutes to set up the steer support. It takes 200 minutes for you to produce 200 steer supports, right? That's 500 up to 460 minutes. Then it takes you another 60 minutes for the next support. So that's the 520 minutes that we're talking about here. So if the milling machine produced one batch after the other without any idle time in between, it would produce 200 components every 520 minutes, right? Which is much faster than the assembly time, which we don't need. So if you keep doing this, then by the time you finish assembly at the end of the day, you will have some inventory left over because assembly is slower. That's why there is 80 minutes of assembly time added in. How do we know it's 80 minutes of assembly time? Because you only can produce one component every 3 minutes, right? So if you have 600 minutes, then you can produce 200. So for 200 components, it takes 600 minutes. So you need 80 minutes of idle time here. Okay. So we can calculate the average inventory and so on. So the key question is, you cannot have a very large batch, but you should not have too small a batch either, right? So if you want to reduce inventory, we need to have smaller. So what is the optimal batch size in this case then? What is the actual batch size that we should produce? So capacity of the bottleneck step is extremely valuable. So that what tells us exactly what we are going to do. So let's take this example here, right? So here we have for the milling machine, we have a setup time of 120 minutes. It takes 2 minutes per unit. Why 2 minutes? Because 1 minute to make the steer support and 1 minute to make a pair of ribs. And then you have the assembly process where the per unit time is 3 minutes per unit to assemble them together, right? So that's the assembly process and then the milling machine process. And we have inventory buffer in between. So what is the optimal batch size for this? So if you produce them in batches of 12, so that is, we do 12 steer supports, then 12 pairs of ribs, 12 steer supports, 12 pairs of ribs, and so on. Then if you remember, we calculate the capacity as 0.833 units per minute, which is less than the assembly process. So if you do this, then the milling machine becomes the bottleneck. But if you produce 300 of these a minute, then the assembly process becomes the bottleneck. So how do we make it so that both of these things are balanced? Well, obviously it's best to make it so that we produce this at the same rate, we produce the milling machine process at the same rate as the assembly process. So we keep the capacity of the milling machine process equal to the capacity of the assembly process, which is a simple mathematical exercise, right? So we need to figure out the batch size. We know that the setup time is 120 minutes, right? And we know that we want a capacity of 1/3. So we want to produce 1 unit every 3 minutes. So we can calculate this out of this using this simple equation. So batch size divided by 120 minutes plus batch size times 2 minutes. And we can say that the optimal batch size is 120 units, right? So it's a simple cross multiply and then calculate the value of B, and we can calculate the proper batch size. This says that if you produce them in batches of 120 units, then you'll have the proper batch size. So you produce 120 steer supports, then you switch over to the ribs. We produce 120 ribs, then you switch over to the machine, and you do this. If you keep doing this continuously, then you'll have the exact matching of the assembly process with the manufacturing process. It's a simple enough calculation, nothing too complicated. So with this, how do you calculate the recommended batch size? So if you do this, if you cross multiply this and everything, so this is what the formula comes down to. So this will be flow rate times setup time divided by 1 minus the flow rate times the processing time, right? So this is the recommended batch size process. So it's the general formula for it. Again, this is not these numbers are not difficult to calculate, right? So that's the basic idea here. So recommended batch size, so 1/3 was what the flow rate was, 1/3 times the setup time, which is 120 minutes, divided by 1 minus flow rate, which is again 1/3 times 2, which is processing time. That gives you the recommended batch size, which is 120. And that's the idea. And if you notice the recommended batch size, so it slowly the processing time will approach the 1 over p, the maximum that you have here, but it will never be exactly 1 over p because we have setup times. And that's the idea. So that's how we calculate the recommended batch size. Now, in the next section, there is setup times and product variety. I'm not going to go over that. It's a simple enough calculation. You can easily go over this. But the end of the takeaway point is that when you have a product variety, setup times and product variety do not mix well, right? So the two obvious solution is that you produce each variety individually, or you can use Henry Ford's approach of you can buy any color Model T as long as it's black. So you produce a single variety and just do that. So this is the reason why, if you remember, Apple does not say produce too many MacBook sizes. So they have 3 or 4 types of MacBooks, and that is all they produce, because setup times for a lot of these production processes are very involved. So you can reduce the number of, if you can reduce the variety, it's much better, especially when you have long setup times. The calculations here are actually very straightforward, so you can go over this on your own. I don't make this longer than 20 minutes. It already is. So I'm going to end here. Now, in class next week, we'll talk about the EOQ model, but that's for in class. So I'll see you all later next week. All right, take care.